of the chapter. And so what we plan on doing is kind of similar to what we did on Wednesday. For the practice problems that we're going to do in your notes, we're going to focus on the practice questions. Because again, the sample exercise questions are pretty similar, and they're already spelled out for you. And that way, we're not just hammering your brains all day today on a Friday. Okay. So what we're going to be talking about today are densities of gases. Okay. We mentioned densities briefly the other day in terms of what I said. They add this note, and it said that, as the molecular mass of gases decreases, so does its density. And that's kind of the idea that we're going to roll with today. But we're still going to incorporate the ideal gas equation. Okay. And so if we take PivNert and divide both sides by volume and RT, we get this setup, where N over V is equal to P over RT. And so that's where we actually begin our journey in how we relate the ideal gas law to the densities of gases. And chapters ago, we talked about molar mass. And we can get molar mass by taking the mass of an object, actually basically looking at the periodic table using the mass and saying that's our molar mass. Okay, mass over moles. Okay, but we can kind of rearrange that equation where we take our moles multiplied by our molar mass to give us the mass of the gas. There's going to be a lot of rhyming today. So if we take molar mass, the capital M from here, and multiply both sides of this equation, we get essentially density. This density, again, earlier in the year, is mass divided by volume. So since density equals mass divided by volume, and now we've got this mass over volume equals P times the molar mass of the gas divided by RT, we can then sit there and say, well, that means density's got to equal pressure times molar mass divided by RT. So we can actually use the density formula up there to help us solve for the molar mass of the gas. This is my second favorite formula. Just like PivNert, it's fun to say it with all the words, or all the letters. So here, ladies and gentlemen, we have dirt P. Say it with me. Dirt P. No one said it with me. Very good. You're going to like saying that. It's going to make you chuckle like it's making Alyssa right now. So that's the basis that we're going to use for when we discuss densities. Okay? And there's a couple different ways that we can use this formula. Well, obviously, we're going to use it to solve for density of a gas. We're also going to use it to solve for molar mass of a gas. And then for our final mathin' that we're going to do, we're going to bring something from chapter 3 or chapter 4. I can never remember which one specifically it is. But we're going to bring back just a hint, just a sprinkle of stoichiometry. Oh, not that word. But it's okay, because the information is already given to you. And when I mention the word stoichiometry, again, it's just a fraction of what we actually have to do. Okay? So let's get into our first practice question. Again, our first one's going to be focusing on calculating gas density. Okay? And we're going to be given very similar information that we've been dealing with for the last, week or so. Okay? So, again, the practice exercises are going to be our focus in class. I highly recommend that you review the sample problem that is on each of these boxes that we're going over. Okay? So let's read this practice problem. The mean molar mass, now that is not meaning that it is angry or not nice, okay? What are we talking about, Kendall? When we say mean in math.
It's about the number, but I don't know what it means.
Okay, right? You know what mean means? Mean defined as, there we go, in math. Okay, Alyssa, 3. It's the average. It's the average molar mass. I just want to do a little alliteration here. Mean molar mass of the atmosphere at the surface of Titan, which is Saturn's largest moon, is 28.6 grams per mole. The surface temperature is 95 Kelvin, and the pressure is 1.6 atmosphere. Assuming ideal behavior, calculate the density of Titan's atmosphere. Okay, so we are off on our adventure of doing some mathin'. Oh, that is not visible. Again, I'm gonna regret doing that, so I'm gonna go one step ahead and do this just to make sure everyone in the back can. Oh, that's even worse. Nope. All right. You see it? Can you see it? Can you see it? Okay. So, what do we know? Well, we're trying to find the density of the gas on Titan. So, we know a few things. Okay, this is what we're calculating for. We know our pressure. We know our temperature. We know our molar mass. That's what that weird looking M is. And we know what R is. R is going to be the same unit. Okay. So, what is our pressure according to this? Our pressure is 1.6 atmospheres, correct? All right. Our temperature was 95 Kelvin. Look at that. It's already in Kelvin for us. So we do not have to do, it's 95, not 9.5. 95 Kelvin. The molar mass of this particular gas was 28.6 grams per mole. And nicely enough, the R value remains the same. 0.08206 liters times atmospheres over moles times Kelvin. Okay, so we are going to use this format of the equation. Since we're solving for density, we can just use this one right here. Okay. There we go. So we're going to take density is equal to M over RT. And since we already have that set up, we go ahead and put our values in. 1.6 atmospheres times our molar mass of 28.6 grams per mole, all over R, 0.08206 liters times atmosphere. You notice I'm going to hold off on putting the moles per Kelvin on here. Okay, we're going to talk about that. It's going to be kind of a reminder. And then times our temperature of 95 Kelvin. Now, excuse me, going back to the R value, again, R is liters times atmospheres over moles times Kelvin. But in its position right here, putting the moles times Kelvin underneath this value, the R value, it's going to give us a denominator in a denominator. We don't want to have that. And so what we can do is simply take the moles times Kelvin, place it over 1, and now we've got moles times Kelvin on top, which will allow for Kelvin to cancel out. It'll allow moles to cancel out. And lastly, atmospheres to cancel out. And so what we're left with is grams over liters. You'll see that here in a minute, which is appropriate for density. Okay, because normally we see grams per mil, okay, for density, but grams per liter is also an acceptable unit. So check my math. As I plug everything into a calculator, I should get that density is equal to 5.9 grams per liter. You all agree with that? See, Kendall is double checking for us. I got 5.9. You got it? Awesome. So again, very similar to, let me get that out of the way. Very similar to Pivnert, where once you make sure you got everything in the appropriate units, set up your equation correctly, plug them in, solve. Okay? Now let's look at how we can use dirt P to solve for another variable. So again, we're going to go to the next sample exercise 10.8. Come on. There, very good. Come on, keep going. All right. So for the practice exercise, we are calculating for the molar mass of the gas. So the question says, calculate the average molar mass of dry air if it has a density of 1.17 grams per liter at 21 degrees Celsius and 740 torr. Okay. Well, we've got a lot of things going on here. So let's take a look. Our density is not going to change or have to be modified at all. It is at 1.17 grams per liter. Now our pressure was at 740 torr. But what unit does it have to be in? Atmospheres. So we have to convert this. So going back early in the chapter, where we take 1 atmosphere over 760 torr, and torrs cancel out, we should get 0.97 atmospheres. So now we've got our pressure in the appropriate unit. Excuse me. What was the temperature in Celsius again? 21. Okay, so we have 21 degrees Celsius, but again, we got to convert that to Kelvin. So add 273. And we should get 200. No, that's not even a 2. That's a 9. 294 Kelvin. The molar mass is what we're trying to find. And again, our R value gets to remain the same, 0.08206 liters times atmosphere over moles times Kelvin. So since we're solving for molar mass, we get to use dirt P. So we set up our equation. Molar mass is equal to density times R times T all over P. And like before, once we have it set up the appropriate way, we go ahead and plug in our unit, our values. So density was 1.17 grams per liter. R again is 0.08206 liters times atmospheres over moles times Kelvin. You can't see what I'm writing. And our temperature was 294 Kelvin. And all that will be divided by our pressure of 0.97 atmosphere. So again, I always appreciate some double checking of work. We should get a molar mass of 29.1 grams per mole. Yeah. I like it when we double check and triple check. Okay back there? All right. Questions thus far? Anybody? Nope. Okay. We've got one more practice that I want to do. And this is the one that, again, we use a very small hint of stoichiometry. But the only reason I say stoichiometry is because we have to relate the coefficients in a balanced chemical equation to help us solve for a particular component. All right. What's nice is that's given to you. Okay. So let's take a look at our final practice question here. Question 10.9. So again, we're going to relate a gas volume to the amount of another substance in a reaction. So we haven't seen one of these in a while, a flow chart. Okay. So here are kind of the steps. Okay? And just if you want to, you can cross out these. This is specific for this particular question, but you're always going to start off with your gas data. Like what information do we know? Okay. So then you're going to go from moles of gas A to moles of gas B to grams of gas B. Okay. Can you read what that says? Okay. Excuse me. And so there's going to be situations that you need to decide. Are we using PivNert or are we using dirt P? And it all comes down to what information are we given? What are we trying to solve for? Okay. So let's take a look at our question here. All right. In the first step in the industrial process for making nitric acid, ammonia reacts with oxygen in the presence of a suitable catalyst to form nitric oxide and water vapor. And we see the balanced chemical equation for this process right here. We are asked how many liters of NH3 at 850 degrees Celsius and 5 atmosphere are required to react with 1 mole of O2 in this reaction. Okay, so right off the bat, we see that we have a temperature, we've got a pressure, and we have moles, not molar mass. So if we have moles, that should lead us to the idea that, okay, PivNert has the variable N in it, which is moles. So for this question, we are going to use PivNert, okay? So let's begin. Writing down what we know. R, and, P, and N. Okay. Well, we're given that the pressure is 5 atmospheres, and that's the appropriate unit we need. Okay. Volume is what we're solving for. Again, R 0.08206 liters times atmospheres over moles times Kelvin. Temperature was 850 degrees Celsius. I believe he's double checking. Yes. And so that's not in the correct unit. So we must take 850 degrees Celsius, add 273, and we should get 1123 Kelvin. Please check. Okay, good. And now that just leaves us with mole. Okay. So we have to do a little dimensional analysis, a little stoichiometry to help get from gas A to gas B. Okay. Gas A is given to us in the problem itself. It says 1 mole of O2. So we write down our given. 1 mole of O2. And in order to go from gas A to gas B, we then refer to the balanced chemical equation. Okay. We have to use, if you recall, the term mole ratio. And the mole ratios are these coefficients here. And so NH3 is the gas B. It's what we're trying to find. O2 is our gas A. So we see that we have 5 O2 and 4 NH3. So that's our mole ratio. So we have 5 mole of O2. That goes on the bottom because we need to cancel that out. And 4 moles of NH3 goes on top. And so now we have now gotten to the step where we are at the number of moles of gas B. And we should have 0.8 moles NH3. Questions on how I got N? Okay. Well, excuse me. Like I said, we're going to be using Pivnert and rearranging it to solve for V. So we're going to take both sides and divide it by pressure. So we get V is equal to nRT over P. And now we can begin plugging in our values. Again, N was 0.8 mole, R 0.08206 liters times atmospheres over moles times Kelvin times our temperature of 1123 Kelvin, all over pressure, which was 5 atmospheres. So after you plug everything in, we should get 14.7 liters of NH3. So I'm going to give you time to double check. Bless. Good there? Good there? Awesome. If you can't read my chicken scratch, just let me know and I'll I'll clarify what everything is. Well, that wraps up densities of gases. Okay. So again, it's not necessarily any different than PivNert, what we've been doing for the last week or so. Just you're incorporating different values. Okay. Questions on any of this, what we covered today? Again, I always highly encourage you to, when you have a moment, those sample questions that are part of exercise 7, 8, and 9, just go over the question, go over this, how they solve it. They explain it in great detail. See how they do it mathematically. Okay, it'll be a great benefit to you. Well, I'm going to go ahead and stop this recording then.